All right, so what is the empirical formula? This is the first thing you should probably write down. It shows the most simplified whole number ratio of the elements in a compound. For example, all ionic formulas are empirical.
And we showed you how to reduce them. If it's a reducible ratio, you're making an empirical formula when it's reduced as far as it will go.
Exactly. And then, of course, molecular formulas show all the atoms of each element in a molecule. A molecular formula may or may not be the same as the empirical formula. That just depends on what you're looking at.
What the ratios are. So I have molecular formulas written. There's 5 molecular formulas. We're going to see if the empirical formula is the same or if it needs to be different.
So for the first one, we have carbon dioxide. It's 1 and a 2 as the subscripts. And the
reduce that.
Yeah, the common denominator is 1, so there's no reduction. So the molecular formula and the empirical formula are the same. And then the next one, we have dihydrogen monoxide, or water. Again, you cannot reduce 2 and 1, so it's still H2O.
And the third one, we have dihydrogen dioxide, more commonly known as
Hydrogen peroxide.
hydrogen peroxide.
And now we have 2 2s. So the molecular formula is H2O2, but the empirical formula for this one is just HO. Okay,
We divide the 2 out, and that's the most reduced form.
and then the next one we have, that's ethene, C2H4. 2 and 4 are both reducible by 2, so it would be C1H2.
Okay, so let's look at now we have sugar. This would be a glucose, C6H12O6.
They all have a common multiple. They have several common multiples. For example, you could do 2, which would give you 3, 6, and 3, but then you could reduce it even further. So the common divisor for this one is going to be 6.
Largest common denominator.
So it's 6, so it becomes 1, 2, 1, C1, H2, O1, or O. And that's what an empirical formula does. And that's pretty straightforward, I think. So let's do some examples using it. Okay.
So there's a number of approaches for determining the empirical formula from mass data or from percent composition. We like this approach because it has a little poem that goes with it, which lets you kind of keep the steps straight. So the poem goes like this: percent to mass, mass to mole, divide by small, multiply to whole. So those are the 4 steps in this problem-solving process, and we're going to give you an example problem and take you through those 4 steps for the problem below, which is saying determine the empirical formula. So we want to know, how much C and how much H is in the compound benzene, and we are told the percent composition of carbon and of hydrogen in the compound. So this might be obtained from laboratory results, combusting it or something to figure out.
So those numbers would be our significant figures. We have 3 for the first and 2 for the second. First, as we say, percent to mass, so we have to take 92.3%, and it magically turns into 92.3 grams.
So we could choose any mass we wanted, but it's simple to work with 100 grams as the total mass of the compound.
Yes.
Because it's already in percentage form. So like Mr. Hunter said, you just drop the percent sign, change it right to grams.
And then the next
So
step.
this would be carbon. Sorry, we're going to start a row for carbon. We're going to do a row for hydrogen. And so it's going to be 7.8%. Change it to 7.8 grams of, this is grams carbon, grams hydrogen.
This is where labeling your atoms come in handy.
It helps you keep it straight.
The next one is mass to mole. So I have to take each element and divide it by its molar mass. So we have to divide grams of carbon by its molar mass of 12.01. And then same for hydrogen. We take 7.8 grams and divide that by 1.01, I think it is off the top of my head.
It is 1.01.
So close to that, grams. And the
Small
first one
carbon.
equals 7.68.
Whoops, so our grams divided out, not the 12.01.
Yeah.
7.68?
7.68.
So we have 7.68 moles of carbon.
The other one is 7.7. Keeping to the sig
7.7
figs.
moles
of H.
hydrogen.
And now we divide by small. So what's smaller, 7.68 or 7.7? Well, it's 7.68.
They're almost the same.
They are
They're
almost the same. So divide 7.68 by itself, and you get 1, of course. And
Okay, we
then
get 1.
you divide 7.7 by 7.68, and you get 1.005.
So the bottom line is they're
both
virtually
1.
the same number.
So the empirical formula in this would be C1H1. There is no multiply to get to whole.
Okay, so they come out, that what this number is that we worked out at the end would be basically the subscript that you need to add for that element.
Exactly.
Okay, yeah, now this step here, like Mr. Hunter just said, we didn't really have to do that. Sometimes when you divide by small, it comes out like a 1.5.
Or 1.25. It's those, then you can
So
multiply. But if it's like 1.002 or 1.01, you kind
If
of
it's very
ignore it.
close to a whole number, just let it as is.
All right. More practice with
So
this ahead
we're
here.
going to actually add one more step to this problem.
Yeah.
So remember, this empirical formula is CH, and we're going to go on to the next slide. Okay, so we're asked in this next step to determine the molecular formula of benzene from its empirical formula. And if you remember, we just figured that out. The empirical formula is CH. And they're also telling us one more piece of information which you need to get the molecular formula. We need to know the molecular mass or molar mass of benzene. And they tell us right here it's 78.12 grams per mole. So the one thing you have to keep in mind is the molecular formula is always a whole number multiple of the empirical formula. And so our job is going to be to find the whole number multiplier we need to apply to the empirical formula.
Yeah, so first we need to find the empirical mass of C and H.
Empirical mass.
And in this case, it's going to equal 13.01 or 02 or something like that. So again, it all depends on what periodic table you use.
13.02 grams per mole. That's the empirical mass.
And then you take 78.12 and you divide it by the empirical mass to get your multiplier. In this case, it turns out to be exactly 6. If it wasn't a whole number, it either rounds up to a whole number to become close. So if we have 6, it becomes C6H6.
So we're taking 6 times CH, kind of algebraic, and we're just going to distribute that through. There is our molecular
formula.
So you just divide them to find the whole number, and it should always come out to a whole number.
Yep.
If they are the same,
Then,
then you know the multiplier is just 1. The empirical formula and the molecular formula are the same. If it comes out a whole number, like it did here, just
Then you
apply the whole
multiply it
number to the empirical formula.
right, a little more practice on the next slide.
So here's the next problem. Rubbing alcohol contains 60% carbon by mass and 13.4% hydrogen. The remaining mass is oxygen. And the molar mass of rubbing alcohol is 60.1 grams per mole, and we are asked to determine the empirical and the molecular formula of the compound. So I've already started setting this up. The first step is change percent to mass. So I took 60% carbon and I just made it 60 grams carbon. 13.4% hydrogen, and I made it 13.4 grams hydrogen. And now the remaining problem is to figure out how many grams of oxygen. So we know that there's 3 things, carbon, hydrogen, and oxygen, and they have to add up percentage-wise to 100. So the first thing we do is we need to take 100 minus 60 and minus 13.4 to determine what the percentage of oxygen is. So if you do that, you come out with 26.62%, or we just change that to 26.62 grams of oxygen. So we've covered the first step, percent to mass.
Yeah. So now we go from mass to mole.
So again, it's just a simple mass to mole conversion. A mole of carbon, 12.01 grams. a mole of hydrogen, 1.01 grams. Right off the periodic table, mole of oxygen is 16.00 grams. So we divide all those masses by the molar mass.
You find out the first one is 3.006.
3.006 moles.
And then the next one
Carbon.
is 7.993.
7.993 moles hydrogen.
And the last one is, of course, 1.
1.00 moles oxygen.
So then if you take these numbers, they're all basically whole numbers. It's 3, 8, and 1. So I would say the empirical formula is C3H8O. And then we have to figure out the molecular formula from this. So I would add all C3H8O up. So it's 12 times 3 plus 8 times 1 plus 16. And we get a empirical mass of 60.11. And then you look up at what it says in the question, which is 60.1, and you say, hey, the empirical formula is the molecular formula. So C3H8O is the answer for this question.
So it's the empirical formula and it's the molecular formula.
All right.
It's one and the same.
All right, and then this last example here, we have a compound with the empirical formula CH2 and a molar mass of 112 grams per mole. They want to know the molecular formula. So the first thing you do is you take CH2, you find its empirical formula, which happens to be 14.03.
You meant the empirical mass, right?
Yeah, that one. Empirical mass to be 14.03.
And that's not the same as 112.
That is not the same, so we know there's going to have to be some additional math.
So we're going to take 112
and divide that.
Divide it by 14.03 to see if we get a whole number multiplier.
And you do that, and you find you get 7.98.
Which is doggone near 8.
8. So I would say the multiplier is 8. So you get C8H16, which is octene. Gotta love that. And if you add those together, I do believe it comes out to be 112. So
yeah, that would be a good check. Does C8H16 add up to 112? And I think you'll find that it does.
It does. So
all right.
We're all good to go there.
So that's the basics of the problem. It's a little, there's more steps involved here, but it's a process. Percent to mass, convert mass to moles, divide by the smallest of the moles in order to get the whole number coefficients or the whole number subscripts. There's your empirical formula.
Yeah, these are very mechanical. They're not really, you have to call upon lots of extra knowledge. You just kind of have to know the steps and to practice these steps.
And it helps if you kind of understand the big picture and what you're doing and why you're doing it.
So if you practice the steps and you continually practice the steps, it'll become second nature to you. If you don't practice the steps, well, you're going to have a hard time. So it's just one of those things. Either that or you memorize that poem Mr. Ferguson made up, so that and Snap.
I didn't make that up,
Oh,
but
you
I
didn't?
stole it from another teacher.
Did you steal Snap too?
Snap? I'm not sure where that came from. I might have made that up, but I doubt it. Somebody else, I'm sure, thought of it before I did.
Anyway, have a good night.
Bye. So here are your post-video questions for lesson 7.6. First of all, what's the empirical formula of the sugar ribose? And we've given you the molecular formula. It's a pentose sugar, which means it contains 5 carbons. C5H10O5 is its molecular formula. See if you can figure out the empirical formula. The second one is going to require a little bit of calculation. What's the empirical formula for a compound found to contain 23.3% magnesium, 30.7% sulfur, 46.0% oxygen by mass? And again, so I'm thinking, right, magnesium, sulfur, oxygen is probably like magnesium sulfate or magnesium sulfite. So that would be kind of what you're going to need to figure out. So remember our little poem, percent to mass, mass to mole, divide by small, then multiply until whole, and at least see if you can set that one up and work it out. See if you can figure out whether it's MgSO4 or MgSO3. And we'll see how you do next time.